Shall we get started? Okay, so congratulations, you made it to the point when we start covering something that's practically useful, namely magnetic resonance imaging. So you now know enough about spin dynamics and its dependence on the various parameters for us to start exploring how MRI instruments work and what we as chemists, as specialists in magnetic resonance, can do to improve that. You've seen in the previous lectures that Fourier transform allows us with considerable ease, in fact, these days, what with all the computers and things, to separate frequencies of a particular oscillating signal. If we would like to record an image, different magnetic properties in different parts of the sample, we must separate spatial locations. And the way to feed it into the mathematical systems that we have already explored is, of course, then to make the frequency dependent on location. If we can separate the frequencies, we would be able to separate locations. So let us think about how an instrument would do that. Item 1 for today is gradients, otherwise known as pulsed field gradients because of the way the instruments implement them. So we want to map our frequencies into our spatial locations. So we want our omega, so the Larmor frequency of the precessing spin, somehow to depend on the location. And the location here is understood as a three-dimensional vector, x, y, z. Of course, you know where this comes from. This is minus gamma b, where b is the external magnetic field, and there's nothing we can do about the gamma. This is the property of proton as an elementary particle. It comes from the interactions of quarks inside it. I mean, unless we have a particle accelerator, we cannot actually change this. So what must therefore depend on the location is the magnetic field. And if you look at figure 1 in your handout, you will see a giant set of coils. And the diameter of the copper wire in there, you can see, is in the centimeters. So there are colossal currents through those coils. And the intention of those coils is precisely this. We have the giant overall magnetic field of the superconducting magnet, and we hope to perturb it in some predictable way using those additional gradient coils to make it location dependent. And the way it is made location dependent is it still stays on the z-axis, so I will call it B0, as we normally call our z direction magnetic field, and it will be a function of x, y, and z. And it will, of course, have the contribution from our original magnetic field of the superconducting magnet, so the big magnet, supercon. And then what we can introduce in the simplest possible way is the next term in the Taylor series. Here, the terms that would be linear in the coordinate x, coordinate y, and coordinate z. So what we are going to do is make some coefficient gx and multiply it by x, plus some coefficient gy multiplied by y, and some coefficient gz and multiplied by z. And then gx, gy, gz have the meaning of linear slopes of our magnetic field in the three corresponding directions. And these slopes are the functions of the current that the instrument puts into those giant coils that you see there in figure 1. The reason why this is called a gradient is actually mathematical. If we calculate the gradient, so of this B0 that we have of x, y, z, you do remember the definition of the gradient, so d B0 by dx, d B0 by dy, and d B0 by dz. Usually, in fact, a column vector, but I put them as row vectors into the handouts to save space. And if we take these derivatives, we all hopefully remember how to take partial derivatives. The derivative with respect to x is gx, gy, and then gz. literally the three elements of the gradient vector of the applied magnetic field, hence the name. What is important here is to remember that this is coordinate dependence of the field, which is still pointing vertically on the Z. Or because the MRI systems are usually horizontal, pointing parallel to the floor in the main direction of the magnet. So we are not tilting the magnetic field, it's still pointing in the original direction it's been pointing, it's just ever so slightly longer and shorter, dependent on the location. And we can try and visualize this gradient field. So if that's our magnet field direction and that is our x direction, then if we have an x gradient, that means that when gx is positive, the field here is slightly stronger than the field there. So we would say, okay, we have a field here and somewhat weaker and very, very weak, going through 0 and then into the negative. So slightly negative, bit more negative, and so on. And likewise in all other points of the sample. So here, for example, would still be a vector of the same length. Here, then here, a bit shorter, like that, and then there, and there, little here, slightly more there, and slightly more there. So this is the x gradient. You can see the field is still pointing towards the Z, but it depends linearly on the x coordinate. If we are looking at the Z gradient, we will have the Z field, which changes its amplitude dependent on the Z coordinate. So somewhere here, we would have the field pointing down, down, relative, of course, to the main magnet field, down, 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 and slightly closer to the origin it would still point down, but to a lesser extent, so like that. And if our GZ is positive, then in the upper half plane we would have the field that is correspondingly pointing up, so somewhere here it would be like that, relative to the field of the primary superconducting magnet. So this is how this gradient looks as a function of location. So this is the Z gradient, and this is the x gradient. And likewise for the y if we have a three-dimensional sample. What this would do, of course, is exactly what we had set out to do and make the Larmor frequency location dependent. Let's think about what is going to happen when we start recording NMR spectra of even ordinary chemical samples in the presence of such a gradient. What the sample looks like normally, it's just a tube, 5 millimeter NMR tube with extremely well machined inner and outer diameter, so quite precise. And we have our sample, and the sample is of about 2 centimeters in length and 5 millimeters across. If we have a uniform magnetic field, then the Larmor frequency of whatever is dissolved, let's assume we have a single line sample, the Larmor frequency of whatever is dissolved here will be the same as the Larmor frequency if it were here. And even if we haven't mixed the sample properly and there are some concentration variations across the sample, we would still have just a single line because the magnetic field is the same everywhere. So we would have one neat or less neat depending on the quality of the instrument, but a single line picture. Let us now think about what would happen if we put our sample into a Z gradient. At the top of the sample we have the magnetic field that is slightly stronger than the field of the supercon magnet. And so the frequency here will correspondingly shift, right? The absolute value will be bigger, the actual value will depend on the sign of the magnetic ratio, but let's just assume that minus gamma is positive for simplicity. And so we are going to have the same frequency range, omega, but at the top of the sample we will have a greater frequency, so we will have a signal here. And if we have a high concentration on top of the sample, this signal will be higher. At the bottom of the sample, here, we have the field that is lower than the primary magnet field, and so the frequency will be lower. And the signal will be there. Let us now imagine that we have a concentration distribution across the sample. Somebody dropped a droplet of ink, and our concentration goes, for example, like this, as a function of the coordinates. So that will be our concentration axis. So at the top the concentration is high, and at the bottom the concentration is low. What is going to happen is the signal that corresponds to the top slice in here will become taller, and the signal corresponding to the bottom slice will become smaller. And we are going to have, if we record spectra of those individual slices, something like that. But that is actually what we are recording, because simultaneously, in the presence of this gradient, we will have in our free induction decay the high frequency corresponding to this, with the weight corresponding to this high concentration, the low frequency corresponding to that, with the weight corresponding to the low concentration. So what we are actually going to see once we do the Fourier transform is a forest of lines, or once you account for the fact that the sample is continuous, you will see one continuous line. So I have shaded it, but it would look like that, corresponding to the literal image of the sample with respect to the concentration of that substance. And if the substance is colored, then this would in fact quite literally correspond to the image of the optical absorption that sample has, for example. And so you can see that by applying a gradient and using the properties of the Fourier transform, which separates our frequencies, what we did is we made our frequency linearly dependent on location. And then Fourier transform, instead of separating frequencies, started separating locations, and we have a one-dimensional image. So this is the elementary foundation of magnetic resonance. Make your frequency location dependent. We can separate frequencies, therefore we can now separate locations. But let us look in some detail at what is happening to the magnetization in the presence of the gradient of the applied magnetic field. So item 2 for today is gradient spirals. Let us consider a sample where the magnetization is already transverse. We did the 90 degrees pulse and we put it in the transverse plane. So I'll draw us some three-dimensional picture here, and we will take a good look at what would happen to our magnetization. So we have our sample, it is extended. Let us assume it is extended along the z coordinate, and we would have some vectors. And these vectors at the very bottom, let's say we would have that, then slightly higher we would have this, then that, then that, that, and that. All of the same length, say, because the concentration is roughly the same. What is going to happen here is, once we turn on the external magnetic field, or just give them some offset in the rotating frame, they will begin to precess around the direction of the applied magnetic field. But because the field is uniform across the sample, they will precess with exactly the same rate, and they will stay in phase. They will keep pointing in the same direction. Now let us think about what would happen if we turn on the gradient. So I'll try reproducing the same picture. So like that, and then this, and this, so x, y, and z. So at the very bottom we have a frequency that is lower than the frequency of that would correspond to the magnet field. And so let's say this signal, this particular magnetization vector, lags behind, or perhaps our rotating frame is just matched to this vector, and so it is static. Anything higher than that would experience a higher magnetic field because we have a z gradient, and so that vector will start getting ahead. Right, so it will turn ever so slightly. Then the vector next to it will be even further ahead, then the next vector next to it even further ahead, and then eventually you will see that what the magnetization vectors now made is a spiral. Right? Like that. It becomes harder to draw here because it starts pointing out of the board. So that's a spiral. And it stands to reason that the stronger this gradient, the tighter will be the winding of that spiral. And in fact, in typical gradients that we have in MRI machines, there are thousands of turns of this spiral per centimeter. These spirals are really tight. Then it also stands to reason that the longer the gradient acts, the tighter the spiral would also become, right? Because it has greater amount of time to accumulate. That has a formal name, so the tightness of this spiral is measured essentially in the amount of turning angle it has accumulated per unit length of the sample. So the greater the number, the tighter is the spiral winding. And so we introduce a parameter now which is central to MRI, and the reason it comes about is, of course, we can have the x component here to be the cosine, right, so cos, the y component to be the sine, and then we can use Euler's formula for the complex exponential to represent this direction of the vector by a complex number in the usual way. So what we would have is some vector cos kz sine kz, where z is the coordinate of the sample and k is the amount of turning angle in radians per meter which this spiral has accumulated. This has a name, unsurprisingly, called k-value. And the way to represent that a bit better is to say, okay, that's equivalent to cos kz plus I sine kz, and that is the same as e to the I kz. And let us have a good think about what this k mathematically is and what the units would be. Well, this is the turning angle, and it's the turning angle still under the Larmor frequency, so it's some kind of minus gamma b, except the b now comes from the gradient term in the rotating frame, and so our k is still minus gamma. MRI textbooks normally don't worry about this minus because they only work on protons and they just adjust their conventions for the positive direction, but in bigger NMR spectroscopy, of course, different nuclei have different signs of this gamma, and certainly the electron gamma is opposite to the proton gamma, and so by the time you need to start worrying about fairly rare but occasionally done nitrogen 15 imaging, you need to worry about this minus, and so we keep it for posterity because we will need it later for various reasons. Okay, so gamma, and of course our correction to the magnetic field is GZZ, so that's GZ times Z, and this is the property of the protons, that is the property of the applied magnetic field, so the instrument, the strength of the current in the gradient coil, and then the coordinate of the sample. But notice that Z is already present here, so we don't need it here, it's already there. But what we do need here is the length of time that the gradient has been active for. And so let us do the dimension analysis here. So we have, what do we have? Radians per second per Tesla times gradient here. In order to have a Tesla with meters multiplying it, this needs to be predictably Tesla per meter. And then finally seconds. And so that Tesla cancels, seconds cancels, an interesting unit of radian per meter, which kind of makes sense given the physical meaning of this K, because this is an amount of turning that the spiral has accumulated, so radians per meter of the sample. So this location, distance from the origin essentially, where our field correction from the gradient is 0. Okay, so this is K, and so more or less that is it, I would say, mathematically for a significant chunk of modern MRI. So we have this parameter that controls the tightness of this spiral winding. We have the ability to distinguish the frequencies based on their location, and that is the principle behind the imaging. But let us put some formal mathematical polish on it. So item 3, so formal math. What I will do now is redo the problem that we have set up here with location-dependent concentration, but in a formal mathematical notation. So let us say we have a distribution of locations with different concentration. Physically speaking, concentration is probability density. It's the likelihood that if you've plucked the molecule out of your solution, that the molecule belongs to your substance. All right? So the mathematical meaning of concentration, even though chemists don't really think about it that way, is probability density. So we have some concentration distribution across the sample, so we would have probability as a function of Z coordinate. So substance, probability, density. Okay, and then we know that at every location our signal is proportional to this. So it has some amplitude, of course, but we don't worry about that. It has this phase term there. So at every Z, we have the signal that's proportional to the probability of finding something that has a signal in there times the signal term there, IKZ. Okay. But of course the MRI instrument only detects the total magnetization of the sample, and therefore we must integrate this over the entire sample. So the magnetic moment that the instrument sees, and it will be a function of time because something happens, and notice that K here is a function of time there. So it will be proportional, not equal, to an integral, and we assume that the sample is finite. So let's say 2 centimeters here, and there's nothing there and nothing there, so we might just take an integral from minus infinity to infinity there, because we know that the function p of z is what mathematicians call has a finite support. It doesn't goes to 0 at infinity. Okay, so we have our p of z, then we have e, and I will open up k using its definition. So it will be minus I, and then gamma gzt, gamma gzt z, and we are integrating over the sample, right, dz. Who recognizes the formula from the previous lecture? Fourier transform, which is lovely because we know that for every Fourier transform there exists an inverse Fourier transform that gets us our function back. So this is Fourier transform. And you can see here a few things about it. It is an integral over the sample, interestingly, so over the spatial coordinate, and time here is a parameter. So we have started in a way already in the frequency space. Now, what happens in practice is, depending on the instrument and depending on the construction of the coils and the ability of the amplifiers that drive those coils, different instruments can output different amplitudes of the gradient. Which means, of course, that then the experiment has to run for different lengths of time to create the same amount of gradient winding. So this is all instrument dependent. What is instrument independent is the product of gamma gzt, so our k in there. So we can rewrite this in a convenient instrument independent way. We can say, well, okay, k is proportional to time, and so we can just as well make this signal a function of k, which will then be proportional to integral from minus infinity to infinity p z, and I return to the original notation that we had there before we put in the k, e I k z d z. Well, now this is precisely inverse Fourier transform, right, because of the plus in there. And we know exactly how to recover our probability density, that is to take the forward Fourier transform. So our pz is therefore proportional again, integral from minus infinity to infinity, mu of k e minus I k z dk, right, the forward Fourier transform. And so we arrive at the central result of magnetic resonance imaging and at the two very important concepts that we have there. Notice, or rather remember, that Fourier transform is a linear operator. If we have a linear combination of these mu's here, we will get a linear combination of p's, and the other way around. So the set of all p's, and they are images, right? They are probability densities of our molecules here, is mathematically speaking a space, because you can add up two concentrations, you can multiply them by a constant. If you deal with relative concentrations, you can even subtract them, so negative ones still have a physical meaning. So this is called an image space. And this is where MRI images live, so far one-dimensional. This mu of k is an interesting quantity, right? It is the magnetic moment as a function of the length of time that the gradient has acted for and of the strength of that gradient. But still, if we have a linear combination of images, they would correspond to linear combinations of these strange functions, and the place where these functions live is called k-space. And the relationship between K space and the image space is the Fourier transform. So in practice, for one-dimensional imaging, and you will see this as the final stage of multi-dimensional imaging sequences, which we will consider in due course, what the instrument does is it applies a particular gradient of the external magnetic field on X, Y, or Z, depending on which dimension of the sample we are reading out, and it simply records the magnetization as NMR instruments do as a function of time. But because we have a constant gradient acting during that acquisition, what happens is, together with time, we have a gradual increase in this parameter K. So the magnetization is recorded not just a function of time, but indirectly as a function of K. We record it in a computer, we instruct the computer to do a Fourier transform, we obtain our image. You can probably see the great number of technicalities in here. We will cover them in the next lecture. What is the sampling frequency here that we need to apply? Remember the Nyquist condition, right? If our gradient's too strong and our sampling's too slow, we will be misrepresenting some frequencies, and so image will get reflected back. And these are real artifacts that you can see in MRI images if you look them up on the internet. So sometimes if the sampling is not fast enough, they reflect back. There will be questions about the units of time and K here and the corresponding units of distance there. So all of the coefficients here will need to be carefully calibrated, and of course you wouldn't get away with these proportionality coefficients that I've used in the practical magnetic resonance imaging, because you do need precise calibration of distances, frequencies, and so on. But you can see the general outline of the entire method. Okay, so the summary for today is MRI is either surprisingly simple or surprisingly difficult, depending on how comfortable you are with the Fourier transform. But the key thing is the property of the Fourier transform, that it can take a time domain signal and separate out all the frequencies. If we make frequency location dependent, the same Fourier transform will separate out all locations. And so we have imaging. How to make the Larmor frequency location dependent? Well, we simply need to make the magnetic field location dependent. And the easiest way to do it, the one that makes all of the subsequent mathematics possible, is to make it linearly location dependent. Linear in X, linear in Y, and linear in Z. At which point, these three slopes, by the mathematical definition of the gradient, are literally the elements of the corresponding gradient vectors, hence the name. And if we impose such a gradient, so Z gradient in this case, on a sample, we realize that, okay, the top of the sample will have higher frequency and will be here. The bottom of the sample will have lower frequency and will be there. Intensity, as you know, is proportional to concentration, and we will just see an image, concentration image of the sample as a function of frequency now, and it is our responsibility then, because we know how the frequency changes with location, to convert these frequencies into units of distance that will correspond to location. A more formal way of doing that is to recognize that magnetic field gradient winds transverse magnetization into spirals as a function of the sample coordinate. Z spiral is easy to visualize, X spiral is a bit more of a pain, and Y spiral. So this picture will be a bit more complicated, but still they are spirals. And the winding frequency of that spiral, so its spatial frequency, the number of turns, the number of radians per unit distance, is called a K value. And predictably it goes into cosine and sine, and because the argument of cosine, sine, and every transcendental function there is must be dimensionless, If that has the dimension of meters, then this has to have the dimension of radians per meter, because radian is what goes into those. For reasons of mathematical convenience, and also for us to be able to use Fourier transform later on, we use the Argand diagram representation of complex numbers in reverse. We say, well, okay, we have a two-dimensional vector, why don't we represent it by a complex number? So that's our EIKZ. And then K itself comes from just the same equation for the Larmor frequency. So the total angle is gamma times the magnetic field, which is GZ times Z. Z we already have here. And of course, the amount of angle that it has accumulated is frequency times the duration for which it has acted. And so there's a T here as well. So that's the total amount of angle per meter, which predictably has the dimension of radians per meter. Okay, having introduced this parameter, we go into formal mathematics and say, okay, our concentration is, mathematically speaking, a probability density. There it is. And at every Z, we will have the intensity of the signal that is proportional to that probability density times the amount of spiral winding which we have accumulated due to the presence of the gradient. But our MRI instrument does not detect separately, this little slice of the body or that little slice of the body. It detects the entire magnetic field emitted by every proton in the body. And so we must integrate, or well, sum over, and the limit of the sum is an integral, over every location. In this case, one-dimensional. So we have that, and the exponential, we plugged in the K explicitly to demonstrate that such a signal will be a function of time, because K is a function of time. And notice that it kind of looks like a Fourier transform, except this is not experiment agnostic, because every instrument will have a different ability to execute the GZ. And so we collapsed the K back into K here, realized that K is proportional to time, so this signal might as well be a function of K, at which point this becomes dimensionless and instrument independent. And we realized that in fact the transformation is the inverse Fourier transform. Therefore, to recover the probability density out of the mu, we need to apply the forward Fourier transform, which we have seen in the previous lecture. Here's the forward Fourier transform. That is our image that is shown in blue there. So the recipe for one-dimensional imaging: do a 90 degrees, turn the gradient on, record the free induction decay, Fourier transform the free induction decay under the gradient. That's your image. Right. In most cases, the samples have uniform concentration, so you will just have a square. But in the cases when they don't, for example, if you're dealing with a biological sample, you will see a one-dimensional concentration image. Interestingly, magnetic resonance imaging rather rarely uses concentration. It uses T1 and T2 relaxation rates as sources of contrast, but that is the next lecture. Any questions?